Welcome back again. Today we are going to continue our discussion on factor groups. In fact, in the last lecture we talked about normal subgroups of a group, and we learned what are the conditions under which a given subgroups becomes a normal subgroup. Usually, when we suppose we have some group G, and then we are taking a subgroup H, any subgroup H of G. Okay, then we can talk about cosets, and cosets they are of two types. So one left coset or right coset like this, where A belongs to the group. This H is a subgroup, and these are not necessarily subgroup. Okay, that we know. So cosets are not necessarily a subgroup. And for example, you can take, suppose you are talking about some 4Z or 5Z, something like this. Okay. So of course, this is a group. In fact, this is a subgroup of Z. But thing is that when we are talking about 1 plus 4Z kind of thing, then since there is no identity element here, so there is no possibility of this to become a group under multiplication, under addition. Okay. So cosets need not be a group, but thing is that there are some condition when it becomes a group. Okay. So for this, we also seen 2 lectures back that product of two subgroups, if there are subgroups H and K, and this becomes a subgroup of G if HK equals to KH. This we know. So from this we can guess what would be the condition for a coset to become a subgroup. And for that, in the last class, we come to know that if certain conditions are satisfied, then we say that this is a subgroup, and that particular subgroup we named as a normal subgroup. Okay. And what was that condition under which AS becomes a subgroup? Do you remember? Hello. And more particular, a normal subgroup. What was the condition? The condition was that AH equals to HA for all A belongs to G. Okay. So if this holds, then we say that the given subgroup, this G, not sorry, this H, not AH. H is a normal subgroup in G of G. So in that case, we used to write like this: H is normal in G. And other examples, we have also seen that A4 is normal in S4. In general, AN is normal in SN. So this can be established. Okay. So now once we have the idea of a normal subgroup, we can now see what are the importance of this normal subgroup. And one of the importance of this normal subgroup is to define the factor groups. And factor groups are important, and we will see them uh, while uh, while discussing the theory of isomorphism on groups in the next unit. So before that, let us see what we mean by the factor group. Okay, so factor groups are essentially defined for a normal subgroup of a given group. Okay, so once we have a subgroup which is normal in G, then we can talk about factor groups, and we denote it by G by H, or sometimes we use to write like this. Okay. So sometimes one may get confused at left coset or right coset, in fact. So when we are considering coset, we are not taking this H to be normal, but this is a subgroup. But while considering a factor group, we are uh, we are taking much in stronger condition that H is not only a group, but this is a normal subgroup. Okay. So this is a theorem, but before that, before that, we can give definition to it. So definition is that let G be a group, and H be any subgroup which is normal in G. Then the factor group or if because we are going to prove this is a factor group, so sometimes we may not uh, write it as a factor group initially. Okay, but okay, then the factor group is defined and denoted by G by H, and this is a collection of all those elements of the form AH, that is some sets or cosets, okay, where H is normal in G, such that A belongs to G. Okay, so this is called factor group. Sometimes G by H is also called quotient group. Quotient. And of course, until now we have not proved that this set is a group. So to prove that this set, that this quotient set or this factor set is a group, we need to have some operation defined on it. Okay, so for that we have a clue. What clue we have? Yesterday we talked about a result which says that if H is normal in G, H is normal in G, and A, B be members of G, then A, H, and then B, H, that is product of two left cosets, is again a left coset. This is what we proved yesterday. So this gives us a clue for multiplication or composition of left or right cosets. A similar thing holds also for right coset. Okay. And that we can write HAHB. This is equals to HAB. So these are the things. So these are the clue how we can define the product or composition of two elements. So in theorem 9.2, this says that let G be a group and H be a normal subgroup of G. The set G by H, which is called a factor group or factor or quotient group, is a group under operation given by this one. That is the product of two left coset is again a left coset, or in a similar fashion, you can say that a product of two right coset is a right coset. So you can write like this also. There is no problem. HAB. Okay, both are equivalent thing. So let us see how we can prove this. So first of all, one thing we should note. That when we are going to define some operation, we need to verify the validity of that operation. That is, that operation should be well defined. Okay. So once we are taking element AH and then another element BH, they belongs to where? G by H. So essentially, if we are going to operate these two AH and BH, it means we are defining some operation from G by H to G by H, and this will also give us a closure kind of thing, closure property. Okay. So for this, let us define some operation over it. Though they have defined already operation they have given. Okay, so let us see how we can proceed. Define some operation F from, or you can write like this composition kind of thing also, there is no problem. F from G by H G by cross G by H to G by H. Okay, either you can write like this or this, absolutely no problem. By how we can define that elements from here AH and then another element BH. Okay, when they are operated, they are going to be mapped on ABH. So this is the operation we have been given. Okay, or else you can write it like this AH and then BH like this. So this is equals to ABH. Okay, so both are the same, or you can write like this. Then F is, that is the operation is well defined. Well defined. How we prove the given operation is well defined? Do you have any idea? There are two things. One is well definedness, well defined, and there is one kind of thing. Okay, there are two things. Here for well defined, we take fx1 and fx2. That is, if images are same. No, I'm sorry. Like this. If elements are same, then they have the same images. Okay, this would imply that fx1 equals to fx2. And for oneness, what we do? We take the images. If images are same, then this would imply that the pre-image is also going to be same. Okay, so these things need to be verified here, and I'm leaving it to you. You can verify it. Okay, you have now operation. You can take different elements, and then you can try it out. So you can take elements like something element here. You need to take element in image in domain here, and then you need to verify them that image are also same. So you can take A1 AH equals to BH. Okay, AH equals to BH, and some other element you can also take A dash H equals to B dash H. Okay. Yes. And then after that you need to operate this one, because you need to take two elements from here. Then you can talk about A, H, and then A dash H. Okay. This is going to be element here in this set. Okay. And then sorry. Okay. A dash, and then this should be equals to some BH and B dash H. Okay, so this is going to be A dash H, and this is going to be B dash H. Fine. So what is this? This is nothing but image. This is equals to AH, and this is AH, like this. Okay, and this is equals to BH and B prime H. So this proves that this is well defined. Now to prove that G by H is a group, what we need to prove? There are four things we need to show. The first thing, or we can write now, we need to prove G by H is a group. Okay, so to prove this, we need to have identity element. Four things we need to. Of course, closure is established from here only. There is no problem. First, you can write by definition as a closure A H B H. So by definition, what we have? We have A B H. Okay, so this is a closure. This is closure. And then second thing, we need to have identity element. Hello. What we need? We need identity element. E and then H. So when we are multiplying, because H is a subgroup of G, and in more particular, H is a normal subgroup of G. So therefore, EH is not going to affect any element of H, and this is going to be H only. Okay. Okay, but now see AH equals to EH because G by H contains the elements. This contains the element of this form. Okay, so AH and EH. So because H is normal in G, so we have AEH, and AE is nothing but this is A and then H. So when we are operating this from left or from right, similarly you can operate it from left also. So you can write AEH and then AH here. So you are going to get EA and then H. This is going to be again AH. Okay. So in this, what we find that EH, this is equals to H, essentially is the identity of G by H, identity of G by H. So next, what we need to prove? Third, we need to establish associativity. So for associativity, we need to consider AH and then BH. Okay, so let us keep them together. And then we have AVH because H is normal in G. Fine. So here we can write CH. And this is equals to, again, these two are left cosets. So we have AB and then C and then H. Okay. So we have another left coset. Similarly, you can try it out for the right coset also if the operation is defined like this. So what we can write? We can write it like AB, and then we can write we can write A, B, and C. Let us keep them in bracket because A, B, and C are elements from G. A, B, C are elements from G, and G is a group, so associativity will be there. So what we can write AH, and then we can write B and CH in another bracket. So this is equals to AH, and then BCH we can write like BC, BH, and CH. Okay, so this confirms the associativity. So now last thing we need to prove that there is inverse. So how, or do you have any guess what is the inverse? You can consider very much A inverse H. Okay, so let us take some A in AH, one element, and then another element A inverse H. Then you can write A inverse H, and then we have identity H, identity and H, and then we have H, and this is identity of G by H, you know. So similarly, you can write also A inverse H, AH, and then we have A inverse AH, then we have EH, and then H. Fine. So this would imply that A inverse H is the inverse of AH. So this completes the proof. Thus, from above discussions, we find that G by H is a group. Okay, so all we done. Now we have established that G by H, that is quotient group, or sometimes we say that factor group. Factor set is a group. Okay, under the given operation. What was the given operation? Given operation was that the product of two left coset or right coset is again a left coset or right coset respectively. Okay. So let us see. Okay. So let us see next some example we can see. Example, if you take like Z, we know that Z, the set of integers under addition is a group. and 4z, that is multiple of all, multiple of 4, uh, is a subgroup of z. Fine. So we have taken that z 4z is a subgroup of z. Then you can also verify that the 4z is a normal in z. 4z is normal in z. Because this is a commutative, you know that z is commutative. So in case of abelian group, these any, or we can write like this, any subgroup of this form. In fact, Z has all subgroups of this form only. Okay, this form only. So they are normal in Z. Okay. Yesterday we were talking about this. So 4Z is moreover 4Z is normal in Z. So we can very much talk about quotient group. So Z by 4Z, and this has elements of the form some k times 4 times z, where k belongs to the set of integers. Okay, so this kind of coset it will have. Fine. So we can give value to k because you know that we can give different value to k. So if k is 0, then we can write 0 plus 4z, and this is nothing but equals to 4z, all multiples of 4. That is, you can write 4 times n, and n belongs to the set of integers. Okay. And then 1 plus 4z, if you are taking, then we have in this elements of the form 1 plus 4n, and n belongs to the set of integers. Okay. So essentially in this set we will be having 1 and 5 and 9 and dot dot dot, and then also some negative number minus 3 minus 7. Okay. So thing is that you need to find out multiple of 4, that is 0 plus minus 4 plus minus 8 dot dot dot. Okay. And once you are adding 1 in each element, you will be getting element here. So 2 plus 4z, in case of 2 plus 4z, you will be getting 2, 6, and then 10 dot dot dot, and then we have 2 minus 6 minus 10, and so on. Similarly, 3 plus 4z, we have a 3 and 7, then 11, and minus 1, minus 5, minus 9, okay, like this. These are the elements. And further, if you are adding 4 plus 4z, what you are going to get? You tell me what you are going to get. 4 plus 4z. You will be getting this element with the 4 added in each element. So you will be getting what? First place 4, and then plus minus 4. So you will be getting 0 at one place, and 1, 8 and one place. All right, like this. But thing is that you will be finally getting 4z only. You know, you will be getting 4z only, because 4 is absorbed here in this one. Do you remember? Do you remember that when we used to write like this, A H equals to H, okay, if and only if H belongs to A. Do you remember this result? Hello? While we were discussing cosets. Huh? So this was the case because 4 belongs to this 4z, so that's why this is happening. Okay, it will absorb here. So for any in general k, okay, we can divide it by 4. So we must be having k of this form, 4 q plus r, where r is between greater than or equals to 0 and less than 4. Fine. So k plus 4z, this is equals to, you can write k to 4q plus r plus 4z. So this is equals to r plus 4q plus 4z. So this is a multiple of 4, and it has also multiple of all multiple of 4. So this will be absorbed. This 4q will be must be here only. So this will be absorbed here. So we must be having this coset of this form. Okay, we have these many cosets where r can take value. R can take value 0, 1, 2, and 3. You see here because the remainder should be non-negative and less than strictly less than 4. So these 4 cosets we are having here. Okay. Now we can see the in fact this is if we take 4 plus r plus 4z, where r can take value 0, 1, 2, and 3. So in fact z upon 4z, it has these many elements r plus 4z, such that r equals to 0, 1, 2, and 3. So there are 4 elements here. So the question is that how we can make a table, because this has to be a group, as we have proved now, just now. So we can write down first element 0 plus 4z. So this is the 4z is essentially. So 1 plus 4z is another element, and then 2 plus 4z another element, and then 3 plus 4z another element. Here you can write 0 plus 4z and 1 plus 4z, and then 2 plus 4z, and then 3 plus 4z. Okay, so you can add these two. You remember that the operation is AH and then BH equals to ABH. Okay, so this was the case when operation was of multiplication, that is a product. But in case of addition, these cosets must be of this form AH, and then operation is also here B plus H. Okay, and this should be equals to A plus B plus H, like this. Okay, so this should we should remember as a translation of this expression. So 0 plus 0, like this 0, or you can write A plus H, for example, plus B plus H. Okay, so this is going to A plus B plus H, like this. Okay, so this should you should remember how the operation is going on. So 0 plus 0 is 0. So we are getting 4z here, and then 1 plus 0. So 1 plus 4z, and then 2 plus 4z, and then 3 plus 4z. Similarly, this column also we can fill. Okay, 3 plus 4z. So we have one row and one column. So now we can operate these two. So 1 plus 1, 2, 2 plus 4z, and then we have 3 plus 4z, and then 3 plus 1, 4 plus 4z, and 0 plus 4z. 0 plus 4z is nothing but 4z only. So here also 3 plus 4z we have, and then 2 plus 2, 4, that is 0 plus 4z, and then we have 1 plus 4z. Last column, let us see 1 plus 4z, that is 0 plus 4z, and then 1 plus 4z, 3 plus 2, 5, and if divide 5 by 4, we are left with remainder 1. So here 2 plus 4z. So this is the table, Keller table for this quotient group, For clarity, let me draw a line. Okay, so this is the thing. Okay, I think things are clear to you. So you can see that this acts as as the identity element. And what are the inverses? For that you need to mark this, and where is 0 plus 4z, 0 plus 4z. Okay, 0 plus 4z. Okay. Here also you can write 0 plus 4z, absolutely. So 0 plus 4z is self-inverse, and 1 plus 4z is inverse of 3 plus 4z. Here 2 plus 4z is self-inverse. You see these. Okay, and then here again 3 plus 4z is the inverse of 1 plus 4z. Okay, So don't you see that this table is somewhat similar to the table when we are constructing table for Z4, Z4, you know, Z4, okay. The group of residues or group of integers multiplication modulo 4. So we can write 0, 1, 2, and 3. So 0, 1, 2, and 3. So 0, 1, 2, 3, 1, 2, 3. And then we have 2, we have 3, we have 0. Here we have 3, and then 0, then 1. And here we have 0, and then 1, we have 2. Okay. So if we compare these two, you see first place 0, here 0, and then 1, 2, 3, only just to see these numbers, okay, just see these numbers. And we have here 1, 2, 3. Similarly, you can see here also 1, 2, 3, and 0. So we have 1, 2, 3, and 0. 1, 2, 3, and 0. Here 2, 3, 0, and 1. You can see 2, 3, 0, and 1. And then 3, 0, 1, and 2. 3, 0, 1, and 2. Okay. So the table is quite similar to Z4. In fact, surprisingly, that this becomes same as or similar as to Z4, that is Z by Z4Z, it becomes similar to Z4. Okay. In fact, we will see later on that they are isomorphic in the next unit. Isomorphic. So isomorphism is what that there are two things. In fact, they are by property they are same, but notations or elements may be different. Okay, just like we read up as 1, 2, 3, 4, 5, 6, 7, the given list of number, and some may say 1, 2, 3, 4, 5, 6, 7, 8, and someone may say in German or French or other or Russian language the same thing. Okay, but numbers are same, but their representation and pronunciations are differing. Okay, so essentially these Z by 4Z, this group is same as Z4, but the presentation or the kind of element they have, their appearance is different. By properties, they are same. Okay. So until now, you have any doubt or what? Okay. So if not, let us move further. So this was in fact the example of from your book. So next example, if you can take G equals to Z18, and let us take H equals to the group generated by 6. Okay, so in 6 we have 0, and then 6 and 12. We can't have more element because you can see Z18 there. Here we are considering Z18 as a group under addition. So therefore 6 plus 6, that is 12, and 6 alone is 6. 6 plus 6 plus 6 is going to 18. Okay, so 3 times 6, that is 6 plus 6 plus 6. This is going to 18, that is 0. So after that, once you add one more 6, you will be getting 6 only. So this is a group. Okay, so here you can verify that because this is Abelian also. So this Abelian, in fact, cyclic also. So H is normal. H is normal in Z, that is Z18. So we can very much talk about the quotient group. What quotient group we can talk about? Z18 over this. Okay. So what kind of element, suppose we are denoted by H, so what kind of element it may have? Okay, it may have element of this form 0 plus H, and then 0 plus sorry, 1 plus h, 2 plus h, like this. Okay, but you see there are 18 elements, so you know that cosets, all cosets here, in fact they are cosets here, so they may not be, they may be exactly same, or they may be totally disjoint, so that we need to verify. Okay, so you can verify, for example, if you are taking 5 plus h, and then you are adding another coset elements, these are the elements from here. Okay, so you can define the operation here also. How you will define the operation? A plus h, and then plus b plus h. This is equals to a plus b and then plus h, like this. Okay, you can write it down like this. This is the operation. So how we can write? This is 9 plus h by definition. So 9 plus h, we can write 3 plus 6 plus h, you know, because h contains all multiple of 6 and 6 belongs to h. So 6 will be absorbed here, you know, a plus h equals to h, if and only if a belongs to h. Do you remember this result? No? Okay. So this is equals to 3 plus h. So essentially these two, once we are having these two, so they becomes like this. Okay. So you can find it out different left or right cosets here using these operation technique. Okay. Fine. So let us, there is one result, in fact important result. Let us try to prove that result. So that result is that when just a minute, wait. There is a result. That result is here. This theorem says that if G is a cyclic group and H be normal in G, then G by H is cyclic. However, the converse need not be true. So converse need not be true. This you can try, or let us see how we can prove this one. Okay, let us see. There is another result. If this is a or if the something is known about G by H, can we say something about G? So that we will see later on. There is another theorem. Okay. So we have been given that G is cyclic. So let G equals to a group generated by A. Okay. Because G is a cyclic. So A is, let us assume that A is a generator of this. Okay. Since N is a subgroup, in fact, one more thing I would like to tell you that if they are simply writing that H is a subgroup, of G, then it is also sufficient because G is cyclic. So all its subgroups will be normal in G. So this should remember. If they are writing like this, then all right. If they are writing like this, then it is also all right. Okay. So this is a stronger condition I have taken here. But if you are writing this, a weaker condition, then also this result will hold. Okay. Since H is a subgroup of G, so H be normal in G. Okay. और अगर नॉर्मल दिया हुआ है then all right, there is no problem, otherwise we need to write like this. ठीक है, कोई दिक्कत नहीं. So G by H is defined, or we can talk about G by H. Okay, we can talk about G by H. So what we need to prove? We need to prove that G by H is cyclic. It's cyclic. So that it means that it is generated by some element. Okay. So G by H. Let us now claim what we claim. We claim that G by H uh, is generated by some element of this form, where A is a generator of G. Okay. So for this, let us see. Let us take some element here. Let X belongs to G by H. G by H. Then X equals to some HG equals to HG for some G belongs to capital G. For some G belongs to capital G. Okay. Now, since G belongs to capital G and G is cyclic, that is generated by A. So this G equals to A to the power M for some integer M. Okay. Now X equals to we have written HG, and this is equals to H A to the power M, and this is equals to H A dot 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 A. So how many times? M times. Okay. So how we can write it? We can write it HA because H is normal in G. So how many times we can write it? M times. M times we can write it. Okay. And then X equals to HA to the power M, because there are M copies. Okay. And this is true for all X belongs to G by H. Okay. So we have taken some element, a particular arbitrary element here, and we are able to write them as a power of some element of HA. Okay. Sorry, an element of HA like this. All right. So this implies what? This implies that G by H is generated by HA. Okay. So this should imply that G by H is cyclic. Now about the converse. For converse part, consider S3. Consider S3. It has element identity 1, 2, 1, 3, and 2, 3, 1, 2, 3, 1, 3, 2, like this. Okay. And this is not cyclic. This is non-cyclic. Non-cyclic. Okay. And then let us consider H. H that is A3. Essentially, we are taking A3. A3, that is all even permutations in S3. So identity 1, 2, 3, and 1, 3, 2. 1, 3, 2. Then A3 is normal in S3. So we can talk about S3 by A3, that is this quotient group. And then the order of this is equals to, this is going to be, because this is normal in A3 is normal in S3. So this is S3 divided by A3, order of this, and this is going to be equals to 6 by 3, that is equals to 2. Okay. Okay. So this would imply that S by 3 and A by 3 is cyclic. Actually, there is a result. I don't remember whether I told you or not. That is, if index G by H of some group in G is equals to 2, okay, then this S3 by not S3 but just a minute. Not index, but we can just a minute. Do you have, okay, we can use some other thing also. We need not to use that one index kind of thing. Order of this is what? 2. 2 is prime. I think this I told you that every group of prime order is cyclic. Do you remember? As 2 is prime. So this this says that the converse of above theorem is not true. You know that though this is cyclic, at that place we came to know that, the statement was that if H is normal in G, for instance, let us see normal in G. Okay, if H is normal in G, then G by H and G is cyclic. G is cyclic. The condition was that H is subgroup of G and G is cyclic. So I'm writing the statement of theorem G by H cyclic. Okay. So now we have example converse. What will be the converse of this? G by H cyclic would imply that G is cyclic. Pakka? All right. So this we have proved, but we have this is cyclic. We considered this is cyclic, but G in our case was S3 non-cyclic. I mean to say that even if the quotient group is cyclic, we cannot say in general that G should be cyclic. Okay. This is a converse part. This is a converse part. Okay. So there is another theorem, not exactly the converse of this, but somewhat related with this. In fact, okay. So next result, you can try it out. That let ZG be the center of G, okay, and such that G by ZG is cyclic, then G is Abelian. So you can try it out. Otherwise, I'll explain. Okay. So we are done. I think you can. There is one more theorem left in this unit 3, Cauchy theorem for finite abelian groups. I'm leaving it to you. You can try it out. Okay. The proof is given in your book in chapter number 9. Maybe this may be, I think, theorem 9.5 or so. Fine. We will be starting in the forthcoming classes from unit 4, the group of homomorphism. Okay. So you can try it out, this one. And this result you can also try it out, or you can once if someone of you are able to solve or pro, you can scan it and send directly me to on WhatsApp. Okay. Okay, I will check and then let you know. Okay, so then I think now time to say bye bye for now.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.